Hello, today we're going to continue Chapter 4. We're going to discuss forces between particles. So last time we discussed Lewis structures and how that applies to the shape of a molecule. And now we're going to apply both of those concepts, so Lewis structures and VSEPR theory, to forces between particles. Now, first, we're going to discuss something called electronegativity. So down below, we have a chart of what are called electronegativity values for common representative elements. Now, remember that covalent bonds are between a nonmetal and a nonmetal. So we do know with ionic bonds that electrons are transferred, but in a covalent bond, electrons are shared. However, electrons are not going to necessarily be shared equally between two atoms. And this depends on how much an atom likes electrons. So you'll notice we have some numbers in our chart associated with each atom. And these numbers range from 0 to 4. So these are our electronegativity values. 4 is the highest electronegativity value, and you'll notice fluorine has a value of 4. What this means is that fluorine really likes electrons. So if it's in a bond with another atom, it's going to hold on or attract electrons more so than the other atom. And then in the opposite corner, we have cesium with a value of 0.7. So a value of around 0 means that something doesn't like electrons and that it could probably give up ownership of electrons to something else. Now, again, here we're talking about covalent bonds or covalent molecules. So we're really just focused on the nonmetals. And the nonmetals in our periodic table are sort of in this region here. And you'll notice that their electronegativity values are about 2 or greater. And remember that hydrogen is also a nonmetal. So if we're trying to determine if one atom likes electrons more than another atom in a covalent bond, we're going to compare those electronegativity values. So unequal sharing of the bonding electrons of a covalent bond cause the bond to become what's called a polar covalent bond. So the way we're going to determine if a bond is polar is by taking the difference between electronegativity values. So let's look at hydrochloric acid, for example, HCl. And here is the Lewis structure for HCl. And now let's go back to our chart on the last slide. So hydrogen has an electronegativity value of 2.1. Chlorine has an electronegativity value of 3.0. Okay, so let's go back to our molecule. So hydrogen had a value of 2.1, chlorine has a value of 3.0. So we're going to take the absolute difference of these two values. So 3 minus 2.1, so that should give us 0.9 as our difference in electronegativity. Now we have a chart in the middle of this slide that tells us whether a bond is polar, nonpolar, or ionic. So if the electronegativity difference is between 0 and 0.4 for two atoms, that means we have a non-polar covalent bond. So we're going to say that the electrons are shared equally between those two atoms. If the difference in electronegativity is in the range of 0.5 to 1.8, that means we have a polar covalent bond. So electrons are shared unequally, and one atom is going to kind of hold on to electrons a little bit more than the other atom. And we just calculated that the electronegativity difference between hydrogen and chlorine is 0.9. So that falls under the category of polar covalent. So here you can imagine a hydrogen atom and a chlorine atom. So electrons are more attracted to chlorine. So that side of the molecule is actually a little bit negatively charged. So we would call that a partial negative charge. And electrons are not as attracted to hydrogen, so we kind of have a lack of electron density on that side of the molecule. So we would say that that side of the molecule is partially positively charged. Another way of showing that is by writing out these symbols. So that's a lowercase delta symbol, and then we're adding a positive or a negative depending on which side attracts electrons more or less. The other way you can draw this is with an arrow kind of pointing towards the side of the molecule that prefers electrons, and then a little positive symbol on the side that does not prefer electrons. So again, hydrogen and chlorine are still sharing electrons. They're just being shared unequally. Now, what if the electronegativity difference between two atoms is in the range of 1.9 to 3.3? That means we have a complete transfer of electrons, and we actually have an ionic bond. So remember, ionic bonds occur between a metal and a nonmetal. So that's another way to tell that you have an ionic bond. But also, let's say we have, for instance, let's say lithium and chlorine. And let's go back to our electronegativity values. So lithium has a value of 1, and chlorine again has a value of 3. So if we take the difference between 3 and 1, we get a value of 2. So I'll put delta En, which is the change in electronegativity, or the difference, is equal to 2. So that means that lithium chloride would be ionic. But also, we have a metal and a nonmetal, so we can also say it's ionic just based off of that fact. All right. Now, again, if you don't have a very large electronegativity value difference, then the molecule will be non-polar. So when the resulting partial charges are distributed symmetrically in a molecule, that's also considered a nonpolar molecule. So for example, let's look at carbon dioxide down below. So we've already drawn the Lewis structure of carbon dioxide a couple of times, and we know that carbon is in the middle, and then it has a double bond with an oxygen on the left and a double bond with an oxygen on the right. Now, if we go back to our electronegativity chart, we can look up the electronegativity values of carbon and oxygen. All right, so carbon has an electronegativity value of 2.5, and oxygen has an electronegativity value of 3.5. So that's a difference of 1. And if we look at our chart on this slide, 1 falls in the range of a polar bond. So let's write out, okay, so we have 2.5 for carbon, 3.5, and 3.5 for each oxygen. So the double bond right here on the left is a polar bond, and the double bond on the right is also a polar bond. However, remember from our discussion of Vesper theory, carbon dioxide is a linear molecule. So those oxygens are pulling electron density in equal but opposite directions. So we could even draw a little picture here. And I'll kind of try to draw the electron density. So it's going to kind of look like a bow tie where both oxygens really like electrons and carbon not so much, at least compared to oxygen. So each oxygen has a partial negative charge, and carbon has a partial positive charge. But again, oxygen is pulling electrons towards the left, and the other oxygen is pulling electrons towards the right. So it's kind of a tug of war. And since both sides are equally strong, we have an overall non-polar molecule. So neither side wins, neither side is more polar than the other. So they kind of cancel each other out. However, if we look at water, the partial charges are distributed non-symmetrically. So that molecule is polar. So water, we might draw the Lewis structure like this, which does look symmetrical. However, lone pairs of electrons like to be next to each other because lone pairs of electrons tend to take up more space. So if they can be closer to each other, then that's more ideal. So I'm going to actually redraw this molecule. So water actually looks like this, where we have the two hydrogens on the bottom, or kind of next to each other, and then the two lone pairs are on the top next to each other. So earlier we said that the electronegativity value of hydrogen is 2.1, and oxygen is 3.5. So the difference, if we're just focusing on the bond on the left, that difference is going to be, let's see, 0.9 plus 0.5, so 1, so that's going to be 1.4, and that's going to fall in the range of polar covalent. And then on the right, we have the same difference, 3.5 minus 2.1, so that's 1.4. So both of those bonds are polar bonds, and electrons are moving up towards oxygen. So down here you can see we have a partial negative side of the molecule, which is towards oxygen, and then a partial positive charge down by the hydrogens. And on the right, we have what's called an electron density map of water. And the blue side is partially positive, so there's a lack of electrons. And the red part is partially negative. So that tells us that there's a lot of electrons hanging out on that side of the molecule. Now, because electrons are not evenly distributed along this molecule, that means we have a polar molecule. Now, let's summarize the different types of forces that can exist between molecules now that we know about covalent molecule polarity. So ionic and covalent bonds represent just two of the forces that occur between atomic-sized particles. However, there are forces that exist between particles, such as metallic bonding, dipolar forces, hydrogen bonding, and dispersion forces. So we're going to go through each of these different types of forces. So again, ionic compounds, for example, sodium chloride, are held together by ionic bonds, which are attractive forces that hold together ions of opposite charge. Polar covalent compounds, such as water and carbon monoxide, are held together by what are called dipolar forces. So these are attractive forces that exist between the positive end of one polar molecule and the negative end of another polar molecule. So for instance, carbon monoxide has a Lewis structure that looks like this, where there's a triple bond between carbon and oxygen. And remember that carbon has an electronegativity value of 2.5, and oxygen has an electronegativity value of 3.5. So if we take the absolute difference, we get a value of 1. So that tells us that carbon monoxide is a polar molecule. So we could even draw a little arrow showing that electrons are more attracted to oxygen and less attracted to carbon. Now, what if we have what if we have an entire container filled with carbon monoxide? How would those different carbon monoxide molecules be attracted to each other? So let's say we have another carbon monoxide molecule. It is going to orient itself so that the positive end of the second molecule is attracted to the negative end of the first molecule. So there's a force between that carbon and oxygen, because remember, the carbon is partially positively charged and the oxygen is partially negatively charged. So those two are attracted to each other, kind of similar to an ionic bond, except we have partial charges instead of full charges. All right. And that goes for other polar molecules as well. They're going to orient themselves in such a way that the positive end of one molecule is facing the negative end of another molecule. Now, some polar molecules, such as water, experience what's called hydrogen bonding. And this is the result of attractive dipolar forces between molecules in which hydrogen atoms are covalently bonded to very electronegative atoms. So those very electronegative atoms are oxygen, nitrogen, or fluorine. So to summarize that, if you have a nitrogen-hydrogen bond in a molecule, or an oxygen-hydrogen bond, or a fluorine-hydrogen bond, those are all hydrogens that can experience hydrogen bonding. So on the right-hand side, we have a figure showing multiple water molecules near each other. And we already said that the hydrogens are partially positively charged because they don't like electrons as much as oxygen. And then oxygen does like electrons more so than hydrogen, so the oxygen side will be partially negatively charged. So if there's a bunch of water molecules near each other, they're going to orient themselves so that the partially positive hydrogens are pointing towards partially negative oxygens. However, because oxygen is very electronegative, if a hydrogen from one water molecule is facing the oxygen of a different water molecule, they're going to form a hydrogen bond. So this is a special type of dipolar force that's even stronger than a dipolar force. All right, and one easy way to remember when hydrogen bonding occurs is to hold the phone. So hold the FON. So if you have a hydrogen bonded to fluorine, oxygen, or nitrogen, you have the potential for a hydrogen bond. All right, and then network solids are solids in which the lattice sites are occupied by atoms that are covalently bonded to each other. So this is kind of a special type of bonding. So for instance, silicon dioxide is present in glass, and silicon dioxide will end up taking the place of a crystal lattice point. So we end up forming this solid that has a network of silicon dioxide molecules. And same goes for diamond. So on the right-hand side, we can see the structure of diamond. And diamond has carbon atoms that are all covalently bonded to each other. And they end up forming this crystal lattice, but instead of ions, we just have carbon atoms. Now, metals are held together by metallic bonds, and this originates from the attraction between positively charged atomic kernels that occupy lattice sites and mobile electrons that move freely through the lattice. So if we have, let's say, a sample of lithium, so just pure lithium, what ends up happening is all of those lithium atoms that are right next to each other are going to form what's called a sea of electrons. So we end up with a lot of positively charged lithium atoms surrounded by a bunch of electrons. And those electrons are just moving around, and that's what's really holding everything together, is that sea of electrons, but also the negative and positive charges that occur. Now, nonpolar covalent molecules like oxygen and carbon dioxide, those are only held together by what are called dispersion forces. So dispersion forces are very weak attractive forces acting between the particles of all matter. And this results from momentary non-symmetric electron distributions in molecules or atoms. So, for example, let's say we have a helium atom. And remember, helium has 2 electrons. So let's say originally the 2 electrons are opposite each other, so they're symmetrically distributed around the atom. But what if, for a brief moment in time, those 2 electrons are on one side of the atom? that's going to create a partial negative side of the atom and a partial positive side on the other side of the atom. So what we get is what's called a temporary dipole or a dispersion force. Now, this is going to cause the other helium atoms nearby to also have a temporary dipole. So for instance, if we have a partial negative charge on the left-hand side of our helium atom, that's going to repel the electron in the other helium atom. So we'll end up with a partial positive and partial negative charge on the second helium atom as well. And again, this is a very temporary force that exists between atoms or molecules. And it does occur in all types of molecules and all types of atoms. But it only happens instantaneously, and it's a very weak force. So again, this is called a dispersion force. Okay, so let's go over a few examples. Now, first, let's kind of rank the different forces we just talked about. So dispersion forces are really weak. And then the next force is a dipolar force. So that's a little bit stronger than a dispersion force. And then next are hydrogen bonds, or H bonds. And then the strongest force is actually an ionic bond. Although there can be, so covalent bonds are also really strong. So ionic / covalent, we'll put there. All right, so that's our ranking of those different forces. To be honest, I'm not sure where metallic would fit. Probably with ionic and covalent as well. So let's go over these examples and figure out what type of force would occur. So let's start with potassium. So if we have a sample of potassium, that means we just have a bunch of potassium atoms all hanging out next to each other. So, you know, it might look something like that. And we saw potassium in a video before, and we saw that it's metallic and shiny, and it's just in the form of a solid. So this would be a metallic bond. So remember, we would actually end up with positively charged potassium ions surrounded by electrons. And those electrons are just freely moving around and kind of holding everything together. So something like that. Okay. Now, carbon dioxide we already went over, so remember that carbon has a double bond with each oxygen, and each oxygen still has 2 lone pairs of electrons because we need an octet of electrons for every atom. And we said that carbon had an electronegativity value of 2.5, and each oxygen had an electronegativity value of 3.5. So both of those double bonds were polar bonds. However, because those oxygens were poling in equal but opposite directions, that made the overall molecule non-polar. So we can even draw little arrows here showing the tug of war that's occurring. Now, because this is a non-polar molecule, that means that it can't have dipolar interactions with another CO2 molecule. So I'll draw another CO2 molecule here. So the interactions that would occur between these two CO2 molecules would actually be dispersion forces. So we would see an instantaneous dipole moment. So there might be, because remember, electrons are constantly moving around. They're not actually static. So maybe some electrons happen to hang out more so on the left side of the molecule for a brief moment. And then that causes a temporary negative charge on that side of the molecule. That would then attract or repel electrons, in the other molecule. So then we'd have a temporary dispersion force that would occur. So remember, nonpolar molecules do experience attractive forces. They're just really weak dispersion forces. All right, now what about NF3? So nitrogen is by itself, so we're going to start by drawing the Lewis structure where nitrogen is in the middle. And then we're going to surround that with fluorines. And I'm going to draw them like this, and we'll see why in a second. And how many valence electrons do we have for this molecule? So we have 5 valence electrons for nitrogen, plus 7 valence electrons for each fluorine. So that's 3 times 7. So we have 24 total valence electrons. So now we're going to start placing bonds between nitrogen and each of the fluorines. And then we want to give an octet of electrons to each of the outer atoms. Or another way to say that, now that we know about electronegativity, we're going to give electrons to the more electronegative atom first. And remember that fluorine is the most electronegative atom. Okay, so we've got NF3. Let's count how many electrons we've used up. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22. Oh, wait. Oh, we have 26 electrons. I made a mistake. You probably are screaming at the screen right now. It's 26. There we go. So we have 2 extra electrons that we need, and we're going to put those on nitrogen, because nitrogen also needs an octet. I'm struggling with math today. It's one of those days. All right, so this is our Lewis structure for NF3. So let's redraw the molecule with some lines for bonds in between these different atoms. There we go. Now, let's figure out if this is a polar molecule or a nonpolar molecule. So if we look at our chart from a few slides ago, we'll see that each fluorine has a value of 4.0 in terms of electronegativity. And nitrogen has a value of 3.0. So if we just focus on each individual bond, the electronegativity difference will be 1 for each bond. So that means that each bond is polar. And electrons are going to be attracted to each of the fluorines more so than the nitrogen. Now, before we actually determine if this molecule is polar or nonpolar, we have to figure out what the geometry of this molecule is. So, how many electron groups do we have? And we're going to look at nitrogen. So how many electron groups are attached to nitrogen? So hopefully you said 4, because remember, we're going to treat lone pairs and atoms, bonded atoms, as the same. So we have 1 lone pair and 3 fluorines, which means we have 4 electron groups. And which shape would this molecule have if there are 4 electron groups surrounding nitrogen? So hopefully you said tetrahedral. So remember, we're going to actually see that we have a fluorine in each corner of a tetrahedron. So remember, a tetrahedron kind of looks like this. So we have a corner at the top and then 3 at the bottom. So the lone pair we'll just put at the top, and then we have a fluorine kind of in the back corner, a fluorine at the front corner, and then a fluorine in the other back corner. Now, another way to draw this is using what are called wedges and dashes. So I'm going to redraw that back bond with a little dashed line. And I'm going to draw this front bond as a wedge. So you can imagine the wedge is kind of coming out of the paper towards us, and the dash is going behind the paper away from us. So that kind of gives the structure more three-dimensionality. Okay, so if this is tetrahedral, let's redraw our arrows showing where electron density is going. So they're all going towards the fluorines. So we can see that electrons are overall moving downward. So maybe we'll draw kind of an overall arrow off to the side. So this tells us that the molecule does have a partial negative side and a partial positive side. So this is a polar molecule. All right, so that's a lot of work, but now we can finally determine what type of force NF3 molecules would have with each other. So if we just had a bunch of NF3 molecules, or nitrogen trifluoride molecules, what type of bond do you think they would, or what type of force do you think they would experience? So hopefully you said dipolar. Now, if you said dispersion, you are technically correct. Dispersion forces exist for all molecules and all atoms. And then if you said hydrogen bonding, that does not occur here because we don't have any hydrogens present. But dipolar forces definitely exist because we do have a polar molecule. So the NF3 molecules would experience mostly dipolar forces. All right. So I'm actually going to rewrite some of this to make some room for our next molecule. So hopefully you took notes. All right, so we said NF3 is a polar molecule. So NF3 molecules would experience dipolar forces between each other. And that's what's going to hold them together. Now for NH3, so you might already be able to tell that NH3 is going to have a very similar structure to NF3. But this time, instead of fluorines, we have hydrogens. And each hydrogen only needs 2 electrons to be happy. All right, so then this is going to have a very similar shape, which is tetrahedral. So I'm just going to draw a very similar drawing from before. So the lone pair is on top and the 3 hydrogens are on the bottom. So let's figure out the electronegativity values. So hydrogen has a value of 2.1. And nitrogen has a value of 3.0. So the difference between each hydrogen and nitrogen is 0.9, and that falls under the category of a polar bond. All right, so each bond is polar. Oh, but did I draw my electrons correctly? No, I drew them backwards. So electrons are actually going away from hydrogen and towards nitrogen, because nitrogen is the more electronegative atom in this molecule. So now if we draw those same arrows on our structure, all the electrons are kind of moving more so towards nitrogen, so we can draw an overall upward pointing arrow. So electrons are going to hang out around nitrogen more often than each of the hydrogens. So this is also a polar molecule. So what type of force is going to exist for this molecule? So if you said dispersion, again, you are correct. Dispersion forces do exist between all molecules and all atoms. But what is the strongest force that this molecule would exhibit? So hopefully you said hydrogen bonds. So remember, hydrogen bonds are going to occur between hydrogens and very electronegative atoms. So those 3 very electronegative atoms were fluorine, oxygen, and nitrogen. So let's say that we have 2 NH3 molecules. Oh, it's not erasing. Let's see, let me get a bigger eraser. There we go. So if we have 2 NH3 molecules, might look something like this. If I can get my pen to work. I'm going to draw these sideways. So they would want to orient themselves so that the partially positive side of one molecule is facing the partially negative side of another molecule. But then additionally, we would see a very strong attraction between the hydrogen of one of these NH3 molecules and the nitrogen of the other molecule. So that would be a hydrogen bond. So even though NF3 and NH3 look very similar, they do both have polar bonds. However, in one molecule, we actually have hydrogen bonded to a nitrogen. So we can have really strong hydrogen bonding. But in NF3, we didn't have any hydrogens present, so we actually just saw dipolar forces between molecules. All right, so just to summarize these different types of bonds, we have dispersion forces, which are really weak. And then as we go up this chart, they're getting stronger. So we have dipolar forces next, then hydrogen bonds. And then at the very top, we have ionic, covalent, and metallic bonds, which are all really strong. All right, so that's actually the end of our Chapter 4 material. We're going to start Chapter 5 in the next video because I don't want to, run out of time and not cover everything this quarter. So I will see you in the next video.